Colligative properties. Number 1, indicate how many particles are formed when the following solutes dissolve. The sucrose is a covalently bonded compound. That makes it a non-electrolyte, so there's only one particle when it dissolves. Sodium sulfate is an ionic compound, and it breaks into 3 ions. You get 2 sodiums and 1 sulfate. Magnesium chloride, also an ionic compound, gives 1 magnesium and 2 chlorides, so there are 3 particles. Methanol is an organic compound. It has 1 particle upon dissolution. Number 2, when 5 grams of calcium chloride dissolves in 50 grams of water, what is the boiling point of the solution? You're given the Kb of water. 99% of the time when you see grams of a compound, you need to convert those grams into moles. So we're going to convert 5 grams of calcium chloride into moles by using the formula mass. Formula mass is found by looking up the atomic mass of each of the elements on the periodic table and adding them together in the correct stoichiometric ratio. So the formula mass of calcium chloride is 110.98. And so you should have 0.045 moles of calcium chloride. Now what we need to do is actually calculate the molality. Molality is moles of the solute divided by kilograms of the solvent. We just calculated the moles of our solute here. And we are given the mass of our solvent, which is the water, and that needs to be converted into kilograms. For a molality of 0.90 lowercase m of solution. Now, the boiling point, the change in temperature for the boiling point is denoted by I, m for molality, K, B. So this is a calcium chloride solution. So our change in temperature is going to be 3 times the molality times the boiling point, the K for water, 0.512, and that's given to you. So the change in boiling point is going to be 1.38 degrees Celsius. So now the new boiling point, this is an increase in the boiling point. Boiling point of water is 100 degrees Celsius. So our new boiling point is 101.38. Number 3, find the boiling point of solution containing 6 grams of benzene and 35 grams of naphthalene, and we're given the Kb. Again, like the problem above, we need to convert these 6 grams of benzene into moles by calculating the molar mass. And then finding the moles, 0.077 moles of benzene. We need to then find the molality. The molality is the moles, 0.077 divided by the mass of the solvent, 35 kilograms, so 0.035 kilograms. We get a molality of solution of 2.2 lowercase m, and we're going to plug that into our change in boiling point solution. So we have I lowercase m and then Kb. So the I here is 1 because benzene is a covalently bonded compound. It's a non-electrolyte, so the I is 1. The molality, we calculated at 2.2, and then the Kb is given to us at 5.65 degrees Celsius m. Number 4, a solution of 26 grams of Epsom salts, which is magnesium sulfate in 1.5 kilograms of water, is prepared. So we need to find the freezing point and the boiling point. Now, both of these require us to find the lowercase m molality, but first we need to find the moles of our Epsom salts. So 26.0 grams of mag sulfate converted into moles using the formula mass. I found the formula mass to be 120.33 grams. And then the moles, I have 0.216 moles of mag sulfate. So the lowercase m, the molality, will be those moles divided by the kilograms of the solvent, 1.5, for a lowercase m molality of 0.144 m of the solution. Now we need to find the delta TF and the delta TB. So I'm going to start with delta TF here. Delta TF is IMKF. I, in this case, we have two particles because this is an ionic compound and it breaks into two ionic species, the magnesium and then the sulfate anion. That's 2 for I, the molality that we just calculated, and then the Kf that's given to us, 1.86 degrees Celsius per molal unit. So the change in freezing point should end up being 0.536 degrees Celsius. Freezing point of water is 0, so the new freezing point will be a negative 0.536 degrees Celsius. So now we do the boiling point as well. Similar equation, delta TB equals IMKB. I is 2, molality is the same, 0.144, and then KB also given to us at 0.512. Work that out, the change in temperature of the boiling point is 0.147 degrees Celsius. So the new boiling point will be 100.147. Calcium chloride is often used to remove ice from roads and sidewalks. Explain how this process works in terms of colligative properties. Well, calcium chloride has this as its formula unit, CaCl2. So that's an I value of 3. We get 3 particles there. An I of 3 will reduce the freezing point more than an I of, say, 1, being sugar, or 2, even sodium chloride. So calcium chloride will reduce that freezing point by getting in between those solvent molecules and preventing them from locking together. Number 6, which salt, NaCl or CaCl2, has a greater effect on freezing point? Well, as I just described, that would be calcium chloride because it has 3 ionic particles to get between those solvent molecules. Number 7, how much would the boiling point of 1 liter of water change if you added 20 grams of sodium chloride to it? Well, let's convert those 20 grams into moles first. Then we can calculate the molality. Now, 1 liter of water has a mass of 1 kilogram. And that's based on the definition of the density of water being 1.00 grams per milliliter. So the molality of our solution is 0.34. We have an I equal to 2. So our change in boiling point would be I times the molality times the KB, which was given to us in a problem above. That's degrees Celsius per molal unit. So we get a change in boiling point of 0.34 degrees Celsius. Number 8, a solution contains 21.6 grams of a non-electrolyte and 175 grams of water. If the water freezes at this temperature with a Kf of this value, which is the non-electrolyte? Well, we're going to back calculate. So if we have our change in freezing point is equal to IMKF, we need to fill in what we know and then solve for what we don't. We're told it's a non-electrolyte, so I is 1. We do not know the molality of the solution, but we do know the Kf of the solution. So we can calculate the molality of this solution to be 3.86 molal units. Now we can back calculate even further because molal, at lowercase m, is the moles of the solute divided by the kilograms of the solvent. Now I know M is 3.86. I do not know how many moles of solute I have, but I do know I have 175 grams, so 0.175 kilograms of water. That makes the moles of my solute equal to 0.6755. So now I'm going to find the molar mass. I know how many grams I started with, and now I know how many moles those grams have to be. Since molar mass is grams per mole, I'm going to take the initial sample, 21.6 grams, and divide it by the moles I calculated, 0.6755. And I end up with a molar mass of 31.98 grams per mole. So now we can do some rough calculating here. If carbon is 12 and each hydrogen is 1, so we have 4 of those, and then oxygen is 16, then that makes this about 32. Here, carbon is 12, so we have 24, plus hydrogen, we have 6 of those, and then an oxygen, so this is going to have a molar mass of about 46. So this non-electrolyte is going to be methanol, CH3OH, because it is very close to the molar mass that we calculated. Number 9, calculate the freezing point of a solution made from 32.7 grams of propane dissolved in 137 grams of benzene. Here's the freezing point. Well, I need to convert those grams of propane into moles of propane by calculating the formula mass found by looking at the atomic masses on the periodic table and then multiplying by the stoichiometric coefficient. So 0.741 moles of propane. So now I need to find the molality. So I take my moles of propane, of my solvent, and I get a molal solution of 5.41 lowercase m. Now I need to do the freezing point calculation. So delta TF is equal to I m KF. The I in this case, propane, is a covalently bonded compound. It is a non-electrolyte, so the I is 1. So I have my molality, 4.51, times the KF, 5.12. And I get a change in freezing point of 27.7 degrees Celsius. Now the original freezing point of benzene, that's 5.5 degrees Celsius. So if I then subtract the change, I get a new freezing point of negative 22.2 degrees Celsius. Number 11, the vapor pressure of water at 20 degrees Celsius is 17.5 torr. So I have my initial vapor pressure, 17.5. What is the vapor pressure of water over a solution containing 300 grams of this compound? You don't have to know what that is, and 455 grams of water. We need to calculate the mole fraction here. So the mole fraction is going to be the moles of water divided by the total moles. So moles of water plus the moles of glucose. This your solute. To calculate the moles of water, we take our 455 grams and use the formula mass in order to calculate our moles of water. And I get 25.3 moles of water. So that number goes here. And that number goes here. Now I need to calculate how many moles of glucose I have as well. So this period here indicates that these zeros here are significant. So we still have 3 significant digits. The molar mass I found here was 180.12, which gives me 1.67 moles of glucose. So finding the mole fraction, I get a mole fraction of 0.938. So now I need to use my change in pressure is equal to my mole fraction times my initial. So now I have the pieces, 0.938 times 17.5 torr, and I get a change of 16.4 torr. Number 12, rank the following solutions from lowest to highest boiling point. So we have a 2.5 molal solution of sodium chloride, a 3.5 of mag chloride, and a 4.5 of sulfur dioxide. So let's find the effective molality here, the I times M. Sodium chloride breaks into two pieces, so 2 times 2.5, we have an effective molality of 5.0. Mag chloride breaks into 3 pieces, 3 times 3.5, we have an effective molality of 10.5. And then the sulfur dioxide is a non-electrolyte. It only has one particle when it is dissolved, and 1 times 4.5 is 4.5. So the highest boiling point is going to be the magnesium chloride, and then, so that's number 1, and number 2 is the sodium chloride, number 3 is the solution with sulfur dioxide. Number 13, if an aqueous solution has a boiling point of 102.5, what is the effective molality of the solution? Well, our change in boiling point is 2.50. We're told it's aqueous, so we are working with a water solution. So I times M times KB. KB has been given in problems above. So that KB value can be substituted. So 0.512. Then you can calculate the I times M. The I times M is the effective molality. So the effective molality here is 4.88 molal units.